Hello, everyone, and welcome to our new webinar on OptiSystem 21.1 and what's new related to photonic designs and simulation features. My name is Ahmed Atiyah, and today I'll be giving an overview about Optiwave. Then I'll show the product line of different software packages. I'll show the new components added up to the new release. Then I'll discuss also the improvements that's been included in this release. Then I'll show the demonstration of the operation of these new components. Okay, Optiwave is established in 1994. And it's located in Ottawa, Ontario. So it's about over 30 years ago. Optiwave develops software packages which can be used for designing, simulating, and optimizing components, the links, systems, and networks. The software can offer the users a distinctive competitive advantage by shortening the product time introduction. So when you do the simulation using the software packages, help you speed up the time to market. It also improves the quality as you do a simulation, investigate different cases which cannot be done through the product, as well as could be enhancing the productivity and cost effectiveness. We offer our software and has been licensed in over than 1,000 industry leading corporates at universities, research, and governmental institutions in over than 80 countries worldwide. Our main product is categorized in 3 categories. The system level, we have 2 software packages. The first one is OptiSystem and OptiSpice. So these 2 software can talk to each other, and you would be able to design with them different devices, photonic systems, optical networks, and so on. In the component level software packages, we have the Opti-beam propagation method, Opti-finite difference time domain method, mode solver, Opti-mode. We have Opti-fiber software and Opti-grating software as well. In the instrumentation level, we have Opti-instrument, which can be used to communicate with equipment remotely or locally, and can be talking to OptiSystem. So you can read data or write data into the equipment, depends on the application. If you are interested in our software, you can go to our website here, optiwave.com, and then go into the download page, 30 days evaluation. So you would be able to download any packages from these 8 software packages. And then once you log on here, you're gonna go into the registration page. Once you register, you'll be able to download any software package. And once you download them, the software will be downloaded into C drive, program files, and Optiwave software. And as you can see here, this is the C drive, the program files, and Optiwave software, and this is the different packages. If you download certain package, you're gonna have the drivers, the documentation folder, and so on. In OptiSystem, we have in the release 21.1 over than 600 components and visualizers in the different domains, in optical domain, electrical, or binary and memory domains. You would be able to design different devices, systems, and so on, and monitor them. And also we have over than 1,000 examples, which can be used as guidance for understanding the operation of the components, as well as building on them for your special design. OptiSystem components include light sources. So we have continuous wave light sources, different types of them, which you can also load your own measure data into these devices. You have light emitting diodes, pixels, DFB lasers, Fabry Bureau, white light sources, and we added up in this release the single photon, or actually single photon laser. You can set up the number of photons you want to transmit. And the optical modulator directory in the component library, you have Mach-Zehnder modulator analytical models, or you can have other models with single drive or dual drive and dual ports and so on. You have electro-absorption modulators, and then phase modulators, amplitude modulators, and frequency modulators. bit sequence generators. We have pseudo-random bit sequence generator and user-defined bit sequence generators as well, and compliance test patterns which can be used for compliances of designing, for example, transceivers. Optical fiber, we have single mode fiber, different types of single mode fibers, and then also we have multi-mode fibers. You can design your own multi-mode fiber and then import it into this component as well. We have also multi-core fiber. You can design single mode multi-core, or you can design multi-core multi-mode fibers. We have electrical modulators. We have orthogonal frequency division multiplexing modulators, quadrature modulators. In the modulation formats, we support almost every modulation scheme available in the market, from return to zero, non-return to zero, duobinary, DBSKs, QAM, PAM, special types of PAM, PAM3, PAM5, PAM7. We have pulse position modulation as well as probabilistic amplitude shaping. So you would be able to employ the probabilistic amplitude shaping on the PAM or the QAM. We have optical electrical filters, including FBGs, fiber Bragg grating filters, and we have optoelectronic circuits which can be designed through OptiSpice and included in OptiSystem. Signal processing, we have a huge library of signal processing, including universal DSP, which has multifunctionality in it. We have equalizers, different type of equalizers. We have data recovery, clock recovery, and 3R regeneration, including the data recovery, clock recovery, as well as the amplitude recovery at the same time. We have different types of forward error correction. We have Reed-Solomon algorithm, low density parity check, and then also we have different mapping schemes which can be used in the system. Detectors, we have bend detector, we have ABD detector, and then we have a single photon detector as well. Optical amplifiers, we support all types of dope material from erbium, terbium, tholium, praseodymium, holmium. We have semiconductor amplifiers. We added up a new component. We're going to show it to you where you can drive this with DC bias or an AC bias. Raman amplifiers, gain flattening filter. We allow optimization for amplifiers or any other parameter or component in OptiSystem. There is different algorithms for optimization you can use. There is waveguide amplifier, erbium, terbium waveguides. Electrical amplifier, we have transimpedance amplifiers. We add up a new component here, allowing users to add up distortions, nonlinear distortion into the amplifiers, limiting amplifiers, and automatic gain control amplifiers. Passive modules, we have almost everything you need to build your system, from couplers, muxes, demuxes, red waveguide switches, attenuators, circulators, isolators, polarization controller, the components, etc. Lots of those components are available in OptiSystem. In multi-mode applications, as I mentioned, we offer multi-mode fiber as well as multi-mode amplifiers. So you can do erbium doped multi-mode amplifiers as well as terbium doped multi-mode amplifiers. We have devices which you can add up to convert the single mode into multi-mode with different types of modes, structures. We have passive multi-mode components, spatial visualizers, which you can monitor your beams and modes. In terms of channels, which you can transmit your data on it, we have the fiber, we have models for Li-Fi, we have models for satellite channels, free space optic channel, visible light communication channels, underwater optical wireless channels. Visualizers, as I mentioned, there is optical, electrical, binary, memory. There's other test sets which you can use in OptiSystem, like BERT, bit error rate test sets, and also light wave analyzers and network analyzers. All these components, or not all, most of these components can be used in a unidirectional or a bidirectional. So you allow transmission of the signal into west to east and or east to west, depends on the application. And also we allow single polarization or dual polarization simulation in our software. Example library, it's, as you can see here, we have, as I mentioned, there is over 1,000 there's over 1,000 examples, which are characterized, as you can see here. It depends on the applications. And in each directory, you can have subdirectories which addresses the different applications. In the advanced modulation directory, you can have examples on QAM, different types of QAM, BAM, and so on. There is applications for new radio front haul applications. There is examples on amplifiers, different types, and optimization of the amplifiers. There's examples on microwave photonics, on sensors, different types of sensors from OTDRs, Phi OTDR, FBGs, the tilted fiber Bragg gratings. We have photonic crystal fiber examples for biosensing and so on. In terms of the wireless communication, there is example on Li-Fi, visible light communication, satellite, underwater communication. As you can see here, almost every application in communication, you have an example which helps you to build on it and learn how to use the components. In terms of spatial division multiplexing, there is examples for single mode or multi-mode or few modes, and on a single multi-core or multi-mode, single core or multi-core fibers. And there is examples, we start adding up examples on quantum key distribution. So with the addition of the, we did in release 21, where we have the single photon detector and now single photon laser, as well as the enabling some features, or add some features to the visualizers to allow users to monitor and analyze. We would have ability to do quantum key distribution analysis. OptiSystem software is able to communicate with different packages of OptiWave, like OptiGrating, where you can design grating in OptiGrating software and then import the transmission and emission spectra into OptiSystem and use that. Same thing for OptiFiber, for OptiFDDT, OptiMode, and OptiBBM and OptiSpice. So all of those software, in some components, we use them as a single component or as measured file or loaded file. We can load them into the components in OptiSystem. Like, for example, the multi-core fiber devices, we design the fiber using OptiMode, and then we import the files into the component and then use them into transmission. Also, this system can talk to external software like MATLAB, Python, C++, Scilab, where the user can either call software from OptiSystem, or you can call OptiSystem from the software. So the ability to call OptiSystem from MATLAB or Python is the same thing. You can call the Python from OptiSystem. So it depends on the application you want it to do. Okay. So now we move into the new component added up to release 21.1. Okay, so we have, as you can see here, 8 components added. The first one is called Wideband Traveling Wave Pulse SOA. So this component allows the user to bias the SOA with AC current TTL signal, or you can do DC bias. Second component is the mirror reflector. And this component, basically we added up the concept of reflection as well as the roughness. So they can add up the roughness into the surface, and you can also load your own measured data into the component. So you would have, I'm going to show you some examples later on for each component and how to set it up, and show some examples for measured data, for example, by our collaborators at the National Research Council. The single photon pulse laser here, this laser is able to generate single photon or any number of photons you desire based on non-return to zero pulses. So it depends on the sequence of pulses. You can set it up, and then for each pulse, you can set up the number of photons you require. Other components is here, standalone components, these 3 of them. So how it operates, you can use them separately, and the results you can load it into the simulation in other components. Now, this is called index of refraction structure altitude. So this would allow you, I'm going to explain to you the calculation of the CN square at different levels. So if the transmitter and receiver are the different levels, then this would enable you to use the proper value of the CN square. There is components here, tools added up to convert JSON files into data files and data file into JSON file. I'm going to show you the structures just to explain. This kind of tools can be used for instrumentation and adding measured data, depends on the instrument, into the components. Other components here, it's the electrical components, which is the tie nonlinear amplifier, and also the ultra-wideband antenna, which allows you to do microwave photonics. Now, the description of each of these components added, in which library is located, and some of information, you can find it in the release note, which is part of the documentation folder, which you can find, as I mentioned, on the C drive and program files and Optiwave software. So this document, if you download it, you're going to see all this information, plus the details of the release. Now, for any of the components, if you wanted to access the datasheet of that component, how you do it, you go to the double click on the component or right click on the component and go to component properties, and then go to the help button here. You would be able to access the datasheet of that component. Also, you can access the datasheet through the document called OptiSystem Component Library. So this has all the components in OptiSystem and visualizers, and with the detail similar to what you find on the help in a single document. In this part here, I'm going to show you the main improvements in the release 21.1, which includes, first thing is the addition of a specific tab for the autocorrelation function. Before, it used to use the same tab of the display. If you go here into system, just to show you, if I open system. Now, if you go to the visualizer in Optical and in time domain here, and double click on it, as you can see here, this is the new tab which you can display the autocorrelation. Now, to be able to see the autocorrelation, you need to right click on the component, go to component properties, and enable the autocorrelation here. So it's off. So what you need to do is you need to choose, is it autocorrelation of the field or the intensity? You choose it, and then when you do the calculation, you would get the result. Okay, so now next here is the other addition is on the dual port time domain visualizer. We added up 2 features here. One feature is we added up a dual display of the autocorrelation of each signal on each port. And then also we created a new cross correlation function. So if you go into the OptiSystem here again and into the compare, in the compare you have the dual port here visualizer. You double click on it, you expand it. And once you expand here, as you can see, you would have the autocorrelation double view. So you can see the autocorrelation with the first port, second port, and you can see the cross correlation of the 2 ports, now, signal on the 2 ports. Now, to be able to access them, the same thing, you need to enable them through the feature here, autocorrelation. You need to set it on and select what you need to display, as well as the off here. Okay. Okay, so let's move on. And the other thing which we added up as a main improvement here in this release is the addition of new variables and unit conversion, which this is can help a lot if you are using external component like MATLAB, Python, Scilab. These new variables can be used directly instead of creating your own, and there is some kind of a conflict could be with OptiSystem. So this would make the life easier. Also, we added them up onto the main layout. So for example, what you can see on the main layout here, if you go into add parameters, you can see under here, if you go, this is the new variables added. And if you take any of these variables, you're going to see the new units here conversion. So you can be able to choose your specific units on the variable you need to add, either in OptiSystem or into the external components like, as I mentioned to you, like the MATLAB component or the Python and C++ components. So in these components, if you want to do also add any parameters here, you can add up that parameter and then you can access it in your code, basically. Okay. Now, I'm going to go start now demonstrating the different components added up into OptiSystem. So the first one here is the wideband traveling wave pulse SOA. So this new component added is a spin-off of the old component, which is a wideband traveling wave SOA. And the old component, it uses a DC current biasing for this component. So you go into injection current type here, it was DC, but now you have the option of choosing DC or AC to drive this new component. And there's an example, if you can see it here in the under semiconductor amplifier directory. If I go into OptiSystem, what I did here, all of these examples, I did calculate them earlier just to demonstrate quickly. So this is the component. You double click on it, you get into injection current, you can choose DC or AC, and you can set up the peak. If it is AC, you can set up the peak of the TTL signal. And the time of this pulse is the same time in the main layout, okay? And as you can see here, there is two layouts in this example. The layout here, it is driving the SOA with a DC current with a peak of 0.13 ampere. And the other part here, it's driving it with an AC signal with a peak 0.13 at a rate of set up by this one here is a 10 gigabit per second. So what's happened here is if the driving bias current is 0, then basically the SOA is going to be getting 0. And that's different from the DC current where all these bits coming from the source here is going to be always seeing the same DC bias. So you are turning on and off basically the SOA at the rate set up by the main layout. As you can see here, the current in the case when you have AC current, have only, for example, 2 pulses for this sequence, which is selected here, user-defined sequence. And the other one for the same sequence, you can see that the results are a bit different. So, and again, it's related to the case where you turn on and off the SOA based on the repetition rate. Okay, so next example here, we go into the transimpedance nonlinear amplifier. And as you can see here, there is an example already on the old component, the TIE, the transimpedance amplifier located at Amplifier Electrical under component sample library. And then what we did here, we added up the nonlinear transimpedance just to compare between them. The old design here, it was linear. So you have V output is related to V input using a constant, which is the gain. But now it's a linear relationship here. But we added up a nonlinear relationship, second term and third term, to allow including distortion of these transimpedance amplifiers. Now, in this kind of example here, as you can see, let me lower this one and look at the second example. So this example here, as you can see, the difference, we set 2 cases, one case with same characteristics here. So we set on the second order and third order, we put 0 gain. Now notice here, we did the change on the old implementation. We added up a unit called unitless, and this is for the gain, and then also dB. So you can have either one option. The old component has an issue with it, so we resolve it in the old component and we add it up into the new component. Now, if you have the same gain for both of them, once you calculate them, you can look at the RF spectrum here, and you can see they are matching exactly the same. But once you start to have the nonlinear characteristics here, the gain is like for the first term, second term, and third term, they are different. And you can see the nonlinear effect here. You start to produce new tones, new frequencies, which goes second order and third order harmonics. Okay, so let's move on. Now, the next component we added up, as I mentioned to you, the mirror. And in the mirror, we have added up 4 functionality here. You can choose the operation of the mirror. Is it independent of the wavelength or dependent on the wavelength, which is coming from here? Or you can have, when it is dependent, you have two profiles, constant profile across the wavelength, or you can have a cosine profile, as well as you can add up your own file. Now here you can see the component, we added up the surface roughness parameters and the incident angle, so to be able to allow calculating the reflection properly into these components. Now, this one is case I'm just showing here. I'm going to show it to you in the example. Case where you have constant functionality within the bandwidth of the mirror. So within the bandwidth operation of the mirror, you have a constant reflection here. And outside band, you have another reflection, which you can set up again from the parameters here, the bandwidth and reflection and outside reflection. Now, this is a data measured from the National Research Council for one of these devices, mirrors, which we're going to use them experimentally in one of the experiments we are conducting, our collaboration with NRC to validate our FSO channel modeling and scintillation model. So this is something hopefully within the next release in September, October time frame, we will show experimental validations for our models. And we are creating a new component actually for the FSO channel, which we're going to call it Universal FSO, which has multi-functionality in it. We're going to talk about it later on in another webinar. Okay, so let's go into the mirror example here just to show you. If you go to the mirror, I have 4 layouts here. The first layout, you're going to assume that it's independent. Second layout, it's assumed the dependent, but it's a constant. As you can see here, you can set up the operating wavelength, the bandwidth of the mirror, and the reflection inside the bandwidth and reflection outside the bandwidth, and so on. You can include the surface roughness and so on in this model. The other model here is the cosine model. The same scenario here, you can do the bandwidth and reflection inside the bandwidth, outside the bandwidth, but the reflection of the roughness here is not included in this model. And the last model is the case where you load your measured file from file, and then you have to set up the data file. If you go here, as you can see, for example, the data file we load, the first column here is the wavelength and the unit, we have to specify it, and the second column, and also we have to specify the unit here. As you can see, you can choose different units, and from reflection here, you can choose either percentage or reflection as a number out of 1. Okay, and then what's happened here, the calculation, as I said, I'm sweeping the laser between 1520 to 1570, and then I'm looking at the result here in the report page. This is the case where you have constant. You have other cases where you have inside the bandwidth and outside the bandwidth. And this is with the cosine profile, and this is with the measured data. So all of these things you can play around, and then eventually you can use this component in a free space optic channel or any application you like to have. Okay, next here is the new tools we added up is converting the data file to JSON and JSON to data file. The idea here, this is a standalone components, and they actually run based on once you press OK into the component setting. I'm going to show you how to set it up. You generate the file. So there is two situations here. Once you, for example, when you wanted to convert the data file into JSON file, you need to select the file. Once you select the file and you click anywhere here on the window, these two or these two fields or more fields can be created based on the loaded file. So if the file has 3 columns, there is going to be 3 fields here. If there is 5 columns, it's going to be 5 fields here. And in every field, you start to select the type of the variable on the first column and its unit, and so second column and its unit, and so on. Now, the second part is you set up your JSON file and JSON file information. And then once you press OK, the file is going to be created. The other component is from JSON to data file. It's easier. The thing which you need to do here is you load your JSON file, path, file, and then the file path for the data file. And then once you press OK, this information will be created, showing you how many columns in the file, what is the variables, and so on, okay, and the units. So let's go into the component just to show you here. So if you go into this files, so this one is the convert data into JSON file here right now, because I'm loading the file. It's called mirror data. Once I load it, is again, this field is generated. So I'm gonna go here and go to tools and into this convert data file to JSON. So I'm gonna load it here. As you can see, this is the default. Once, let's say I select the component, I need to do this one here, and I click anywhere. Okay, these two fields are created based on the number of columns here. So the first one, this is the default cases. It's called power. However, I can go change it into, in our situation, into frequency wavelength, and I need to select the units in nanometer, because this is how it is, the data file is existing. And the second field here is reflection, and it is not percentage, it is unitless, okay? And then when I say okay, this file is going to be created, which is this JSON file here. As you can see, there is no JSON file here. But once I said okay, the component is being calculated, and then you can go here and see the components called JSON, okay? This is the new component. Now, the JSON file here, this is where you can set up the name of the file, the path for the file, and so on. And the last one here, you enter your definition how the JSON file should look like, okay? So if you can enter, for example, the ID, the lens number. This is standard from OptiInstrument software, which we were communicating with the equipment from Expo. But you can set up your own data here, as you can see. You can set up, for example, this is, you call it mirror, OSA, NRC, and so on. And this is exactly what is going to happen, appear on the JSON file here. So this is our JSON file, which I created earlier. If I look at it, this is the ID. It's called mirror, it's called OSA, NRC. So this is the format of a typical JSON file. So if the equipment you use generate JSON files, this is how it's going to look like, this kind of fields. And this is the first column. If you if you look here again, the first column and the name of the variable, and then the unit of the variable. Second column, the name of the variable and the unit of that variable. Okay, so this is how the JSON file looks like. The same thing you can do opposite with the convert from JSON file. So the JSON file, what you need to do again is you need to select the JSON file and select the data file. Once you do the calculation, the results appear here. So if you right-click on the results, these results are going to appear. Number of data fields, size of each curve, data on the field, what is the variable, name, the units, and so on. So all of this information will be available for you in the data file, and the data file will be created. Okay, so next here, we're going to go to the index of refraction altitude structure CN square, which is a basic component. Is going to be used for the universal FSO component we are creating in September. But just to show you here what's happening, typically what you can use right now in the FSO channel, you can assume that the TX and RX are on the same level, okay? So the same height. And you're going to assume that the CN square is a number constant, and that number is, okay, the issue right now is you pick up a number, but you don't know what is the altitude you are using for your calculation. So this new component, at least for the time being, this index of refraction structure component would allow you to know what is the CN square constant value at this point. However, if you start to have the receiver and transmitter at different altitudes, then there is another component of CN, which is a vertical one. And this vertical one is going to be defined with, here we have a new parameter we added up into this component. It's called fried parameter. And this fried parameter is going to be calculated using these two equations. Now, the new component here, we have 7 models added up into it. And each model can be, as you can see here, works in different regions. And in different regions can be in daylight or night, or can be analytical, or it can be empirical formulas. So all of these details are in the data sheet. You can find them. And in that scenario here, you can see these different models, how they behave, like in this altitude variation up to about 20,000 meters. Like you have very high altitude when you are at 1 meter above the ground, the scintillation, this is the values within these models, as I mentioned, and this variation in these models. Once you have very high altitude, you don't have very low scintillation, CN square, okay? So let's go into the demonstration of this component. You can see here into the component, it's existing under the free space optics component. As you drag it here, you double click on it, it's a standalone component again. It depends on, you choose the altitude, and then you choose the model you wanted to use. And then depends on the model you choose, these parameters can be gray or can be active, depends on the model. So in some models, as you can see, the ground speed of the wind would take into effect or not, and so on. So this is, once you do the calculation, what's happened is go to the results here, you're gonna generate the CN square value here, which we use to implement to basically show you the plots here. And this plot is based on generating a sweep for the different altitudes, and we created these plots. Okay, so next here is the single photon pulse laser. Again, the single photon pulse laser is based on it's called compound component. So we added up different components to create this component, and this is including the CW laser, the pseudo-random bit sequence generator, the modulator, attenuator, and with that, depends on the setting of the data rate you set up here, depends on the sequence you choose, then you have different attenuation generated here, and this attenuation will enable you to get the proper number of photons you set. Okay, so in this case here, just to show you in the example, you set up, for example, I need 1 photon, and this process is a random process, a stochastic process. Okay, so if you set up 1 photon, you might get 1 photon, you might get 2 photons, or you get 0 photons. Okay, so this is, as you can see, this is the random processes appearing here. And every time you run this component, you might get exact value, or you get another value below or value above, depends on the process. There's 2 random processes here. Is the one process is the SPD process, because this detection is done through the single photon detector, which depends on the Poisson detection process, and also in the randomness generated by these components, depends on the rate, depends on the process. Okay, the equation used to do calculation, we based on this equation. So we set up the number of photons I need, based on number of photons I need, and based on what is coming here on sequence of bits on peak power, and we use here a non-return to 0 pulses, so that T full width at half maximum is exactly the bit period. And then we do the calculation, and then we see how much power coming into the component from the laser, and then based on that, we set up an attenuation to get you the proper attenuation value needed to generate the number of photons. So if you go here into the example we created for the single photon detector here, as you can see, we have different layouts, and this layout on a 10 gigabit per second, second layout on 1 gigabit per second, and third layout on 500 megabit per second. And for each layout, we use exactly the same setting, which is we use a medium refractive index of 1.45. We sweep the number of photons from 1 to 20. And then in the laser, we set up the wavelength, we set up the power, we set up the line width of the laser. In the bit sequence, this is the sequence generator. So you can use your sequence either using alternating You can use explicit, you can load from file, depends on what you need to generate here, the sequence you want to generate. And then after that, you run the simulation and so on. So this is the cases. And this is, for example, the graph here. It's, as you see, this is different graph compared to the one I have in the slide because of the randomness of the detection. Okay, so next here. So next component is the ultra-wideband antenna, and this is mainly a component can be used for microwave photonics. There is an example you can see here at its location, and in this example already in OptiSystem. What we did is we cut up this part because it's going directly into the receiver circuitry, and then we put the transmitter and receiver antennas, and then we detect the signal with that. Now, the transmitter and receiver antennas is exactly the same antenna with the same parameters. The only difference is if we use them as transmitter antenna or receiver antenna, is the equation is a bit different, as you can see here. However, they are supposed to be matching together to give you the best optimized parameter. You can read more about these components in OptiSystem data sheet. Now, in these components requires the S parameters of the devices. So typically you can either measure the S parameter in the lab, or you can using a network analyzer, or you can get it from the vendor who make these antennas. And also you can design the S parameters or design the antenna in a different software and then load the S parameters into OptiSystem. Now the loading, as you can see here, we have two options of loading. One option is when you have measured data as parameters from a network analyzer. This is the equipment used to measure the component. And this component, as you can see here, it has the different parameters, and each parameter is explained in OptiSystem, the units of the column, the resistance values, and so on. Now the columns are organized, as you can see here, S11, S21, S12, S22. So if you wanted to load your own, you have to follow this kind of structure to be able to load it and use it properly. Now, if you go into the example we created here, into the example, as I mentioned, again, we calculate this example, exactly the same thing, but the antenna here, it's a transmitter antenna. You have to select transmitter or receiver, and then you could select the file units here. It's a real, imaginary. There's different options you can have. You can have a magnitude, angle, or phase, or real and imaginary, depends on the data. You have to choose the type of it, and then you have to put the range of that, and then you load the file. This is determination resistance. Now, this data is not measured by the network analyzer, so that's why we enter these parameters manually. Else, if it is from the measured, this will be read from the file directly. Okay. Now, the same thing for the receiver antenna. We choose the receiver antenna and we select all of this information. Now, as you can see here, to distinguish between loading from a network analyzer or from a software is this tab here using hashtag. If you click on it, as you can see here, some parameters is going to be disabled. If it's enabled, it is false, this one, which means a data file is generated using, as I showed you in this slide. Now, you look at the performance of this design right now, you go to the OFDM, this is the bit error rate. Here, there is 3,015 bits error out of 65,000 bits. And the bit error rate is around 10-1. Now, if you look at the symbol and the graph of the constellation, you can see that the clusters of this, and there is lots of close to each other, and then this is related to the design, and then the noises and the antennas and the system. So, but this is, as you can see, there is at least these clusters clear. They are not interacting. That's why still you have a 10-1 bit error rate. Once you have the proper design and the optimized parameter of everything, you should have a better performance. Okay, and then next we're gonna move into the component here. It's called photonic power converter. Now, what is this component? This component is similar to a solar cell, but how it operates is you you incident laser light into the surface of the device, and then this component will convert the light of the laser into electricity. Okay. Now, the component can be a single junction or multi-junction. We did a webinar actually in collaboration with the University of Ottawa and the Fraunhofer Institute, ESA, it's called, in Germany, and also collaboration with National Research Council in Canada, where the component has been designed and manufactured and tested. And actually, we use measured data to create the component model. We used actually a two-diode model in the design of the component, and then we expanded to multi-junction. So this is a single junction two-diode model. And as you can see here, there's different parameters are essential to design the component, which is the J1 current, which is current density J1, current density J2, parallel resistance, series resistance, and the incident light photocurrent. Okay, and then this component can act as a current-dependent source. And this current-dependent source depends on the incident light and the applied voltage to the device. Okay, so as you can see here, if you go back, the current can be negative produced with this device or can be positive, depends, is it absorbing the light incident on it or absorbing it and generating current of it. So it depends on the operating voltage of these devices. Okay, so you're gonna see here, in the component, we have some tab where you enter the parameters, the J01, J02, the series resistance parallel. You can enter them by yourself as design parameters, or you can load measured data. So this measured data, as you can see, I'm going to show it to you in a second. These measured data are dark current measurement, light current measurements at different laser current here or amount of power, laser power hit the surface of the photonic power converter. Now, this component can be used mainly in beaming applications, where you can, for example, use it for power up high altitude balloons or remote radio head, where, for example, you don't have electricity, you can shine laser onto this chip and then convert to current, and then it's like exactly similar to solar panel, but using light. Now, loading the data here, what happens is once you load the data, you can use one curve or multi curves, depends on how many curves you can use them and the combination of these curves to create the, this is the measured data files. As you can see here, we have 7 of them. I'm going to show you, and depends on each one of these curves, you have different power incident on the component, and then we create some kind of fitting. I'm going to show you the fitting here and shows you if your fitting is good or bad, and how is this fitting will produce the 4 parameters, the J01, J02, RS, and RP. Okay, so if you go here now into the example quickly, this one here. So we have in the example 3 layout. So this layout here, we are using the parameters without measured data. So you enter in the number of junctions. You can enter 1 junction, 2 junction. We have actually the guys from University of Ottawa in Germany, Fraunhofer Institute, they demonstrated 10 junctions. So we have data for 1 junction, 2 junctions, 10 junctions, and so on. And you can look at the surface area of the device. You look at the responsivity. You can use your own device conversion or internal device conversion. And then this parameter is very important, is the applied voltage for that device, where you wanted to do the operation of that device. Okay, and then you look at these parameters, and then you can create your graphs for light current. I'm going to show it to you, or dark current, or power measurements. And if you load data, you need to enter parameters for the fitting. Okay, so let me go to the window here for the measuring the data or loading the data. So if you go to the loading the data here, I'm loading, as you can see, 7 curves, and each of these curves you load it from measured data files. Okay, and then you choose what is combination here. Now, once you choose which combination you want to use to do the fitting and generating these 4 parameters, These format methods, if you look at them, they will be updated when I do run. This is a new feature we added up into OptiSystem actually, where you can calculate during the setting of the parameters of the component. Okay, so the release, which is 21.1, actually doesn't have this feature. We added up just about a couple of weeks ago. We're gonna release it in a month for users. But now the old one which you have, you just press OK, and then it's gonna be updating. Now if you press here on it, as you can see, what's happened is it's gonna take time to read the initial guess, the ranges of the guesses, and so on, and start doing the fitting process. As you can see here, it's gonna do the fitting process. And once its fit is done, it's gonna generate this plot for you. And this plot, for every measured curve you load, it look at the fit parameters and see the error of these parameters. And with that, eventually, once you close this one here, these parameters will be updated, okay? And this is once you press OK, the new calculated parameters would be used when you calculate the component. Now, in these three examples here, this component we use zero current, so this is called dark current. And this one here is we applying 1 watt into the surface of the device. And you can see here in the surface watt, we can generate about 80 or 90 milliampere from the device. Now, if you click on the component and go to the project browser here, and you look at the component, okay, so this is the component. There is some graphs you can create, as I mentioned. In the graphs here, you can select the range of voltage, how many data points, and so on. You can set up here, and even you can save the file if you wanted. And then if you click here, this is the current voltage data. This is the dark current voltage data. But as you can see here, because we're applying light, there is no dark current. However, if you go to one of these dark current cases here, you can see the dark current measurements when this is at 0 volt. How much is the current, which is the dark current here, and then there is lots of calculation involved in this device. But again, this is a device mainly used for power beaming applications. The last thing here in this webinar, I'm going to demonstrate quickly, hopefully to get some time for answering some questions, is the new addition to the component, which is optical amplifier measure. This optical amplifier measure, you can think about it as a black box. Actually, this is a very valuable component where you can, if you look at the component under the measured gain and noise figure field here, you can enter measured data for the gain versus wavelength, noise figure versus wavelength, and you can use it as a black box, so it can be applied for any type of amplifier, even semiconductor amplifier, Raman amplifier. You can use it for any kind of amplifier as long as you have measured data. And also you can load different curves with this this feature if we sweep this parameter. So here in this example, which is located in the release under optical amplifier nonlinear directory, I swept about 11 files. And the purpose of sweeping these files, I create manually a nonlinear functionality. So as you can see here, the wavelength range of operation, you can control the gain, you can control the noise figure, you enter it manually, or if you want to create a specific design theoretically, let's say, you can enter this as manually, or it is measured, you can load these numbers from measured. Okay, so you can use the load file. And then eventually you can create, as you can see here, typically with these amplifiers, it's linear amplifiers. You can output and versus input is a linear. And then after that, you have saturation. But this functionality, you have a nonlinear characteristics. As you can see here, the gain versus input power is a nonlinear function. This is, again, I created manually, but you can create your own, or you can load your measured values as I'm going to show you here. If you go into the last example, this one amplifier, you can have, this is the data loaded, but if you have sweep parameter here in each one of these files, you can make sweep, and this sweep data, as you can see, If I open the file folder, you have every file you can enter theoretically again or measured the data for the wavelength, the gain, and the noise figure. So you need to follow up this kind of structure, which is set up in this this field here. So you need wavelength in nanometers. So if you expand here, so in wavelength in nanometer, gain in dB, and noise figure in dB as well. So if you do that and you do the calculation again, you can create whatever the characteristics you require. So you can use it as a black box with measured data, or you can create your own amplifier if you wanted to do that. Okay, and with that, I think this is the last slide, and then I'm open for questions. Thank you for listening. So let's take a few questions here. Okay, so if you have questions here, I'm gonna try from the top. How to generate the S parameters files to an ultra-wideband antenna? Again, as I mentioned in the talk, is typically with this kind of files, you can either measure them or you can get them from the vendor, or you can use the software to design the antenna and then load it into OptiSystem. The most important part is to make sure that if it is hashtag where it is measured, so you have different parameters already in the file, or you need to load these parameters yourself. How to use the ultra-wide antenna as a receiver antenna? Okay, so in the component you have either option of transmitter or receiver, so you have to choose it, and based on that you have the different transfer function added up. Okay, so let's see here. Any chances of adding Kramer's Kronk block? Okay, so the filters we have in OptiSystem different components where you can load your own measured filter design. So there is a component. If you have the filter characteristics, you can load it into that component, and in that component you can eventually use that filter. Now, if you wanted to vary parameters, what you can do, it depends on the H of F you have. You might add up a parameter to it phase, and then you do some calculation inside the component using scripting. Okay, so if you are interested, just send me an email, and I'll talk about this with you in a separate email. I want to process the data collected in the text file or CSV file using OptiSystem. How can I use MATLAB component to do the same? Now again, it's in MATLAB you can in OptiSystem you can load parameters and you can load files into the component. If please send me an email at my email address here, and then I'll show you how to load data into the MATLAB component. For the presentation, okay, so the presentation, we're gonna make it available for the people who register, and my colleague Sawyer, who's the director of sales and marketing, he will be sending the recording as well as the presentation to everyone asking for it. Can I use the photonic power converter as a photo detector? It's actually a photo detector because it detects light and convert it into electricity. However, the advantage of the photonic power converter, it enables the user to use a actual physical device for the detector. Okay. Do you consider other scintillation algorithms in the FSO channel? Okay, so in September or October time frame, as I mentioned, we'll have a new component called Universal FSO channel, and this component has actually multifunctionality added to it. We're going to have in total 5 scintillation model. We have already gamma and log normal. We're going to add up negative exponential, K model, and Malaga model into this new component. Also, we're going to have the scintillation altitude algorithm, as I mentioned. We're going to have bright parameter addition. We're going to have beam distortion implementation. So what also you can do is in this component, you can monitor the progress of the beam along the propagation. So you would have distortion analysis and phase scintillation phase effects into the calculation. And this is, as I mentioned, it's going to be ready by sometime in September, October, release 22 of OptiSystem. Okay. Can we simulate VCSELs with gain performance in Optiwave? Yeah, in OptiSystem there is a component, actually two components in OptiSystem, which are used for designing VCSELs, single mode or multi-mode. You can just show you here quickly. If you go to the directory in the transmitter library, optical sources, you can have, as you can see here, VCSELs, lasers, and VCSELs measured. So there is a lot of flexibility in designing the VCSEL and make it, you can load your data as well and so on. This is for single mode. And we have under the multi-mode library, if you go to multi-mode library here, under transmitters, you can have, you see here, VCSEL spatial. So you can have spatial modes or VCSELs temporal and spatial effects in the VCSEL. So you have 4 components you can use for that. Okay, another question is how single photon laser is different from the CW laser. Okay, so the CW laser, it produces a huge number of photons, depends on the power again. But if you recall, I said the laser depends on the sequence structure, how many the bits of structures and bit rate. Then you can have bare pulse certain number of photons, and that can be controlled using the attenuation. So in this component, the single photon laser, it's a compound component which includes all of these components together and allow you to set up certain number of photons bare pulse, basically. Okay, so there is a few more questions here, and I'm gonna answer them separately because we are almost 2 minutes above the time. I thank you everyone for attending and listening for the webinar. And as I mentioned, we'll share the slides and the recording with everyone. Thank you very much. See you in another webinar. Bye-bye.